We are recording. Welcome to another exciting computer architecture class. Sorry for the late start there. Seem to have had a little technical malfunction. I wanted to go over a couple of dates with you. Let's see if we can't do that right now. Some administrivia, because the end of the semester is coming and people are going to be running away for things like Thanksgiving break and such, and then they won't be coming back. So we're going to have to finish up at a distance after this week. Um, We've got homework 10 due this coming Thursday. It's on the I squared C and distributed computing. So I think we probably beat that one to death pretty good. So hopefully everybody here is up to speed on that. There's going to be a homework 11 due the week that you come back, but it'll be the Thursday following your return. Well, your virtual return, I guess I should say. And then in a couple of weeks, we're going to have a final. And this will be available for you as a date you can write down later, but you should write this down in your calendar because late finals will not be accepted. And the reason why is because as I look at the calendar here, we are basically pushing the end of finals week there. Finals week begins on the 15th. This will be the last Thursday of finals week. I don't think we want to try and push it and get these things late. So I like to get the grades in on time if I can. And so if there's late work that needs to be made up, it's a bummer. And so review your grades and make sure you got your homeworks in. If there's something you didn't do or didn't appear, let me know. We'll get things fixed before grades are assigned. It's always easier to do that now than later. Were there any questions about the homework 10, which is due this Thursday? No questions? I'm just going to scan my list. It doesn't look like we have a full class here. Well, I thought what I would do is a bit of a deeper dive into this new M1 CPU that Apple has. And I know that I kind of was looking at it the other day and I thought it was interesting that they had these, sort of architectural things and artifacts and translate look-aside buffers and all these other little extra things that they added. And I just looked at this and I said, what is going on here with the RAM? And it's looked to me, and I think this is true, you cannot add RAM to the M1 CPU. They just put everything on the same chip. Now, from a computer architecture point of view, we have normally, we have two kinds of RAM. We have, in terms of memory architecture, one is called Uniform Memory Architecture, UMA, and the other is called Non-Uniform Memory Architecture, NUMA. But then Apple comes along with the so-called Apple Unified Memory Architecture trademark. And that's like confusing and maybe marketing. And then it says you get 16 gigabytes of RAM and that's it. And I said, who do you think you're talking to? I've got a soldering iron. And I'll take it apart and I'll add the RAM. I'll just unsolder what's there. And apparently you can't because there's nothing to unsolder. It's all part of the same chip. And I said, no expansion. This is sounding an awful lot like planned obsolescence. I have a neighbor with an Apple Air. It only has 1 gigabyte of RAM or 8 gigabytes of RAM, and it's slow. And I said, well, it needs new RAM. And I look it up and I find out you can't add RAM. You just can't do it unless you're willing to take the whole thing apart and unsolder and then solder in some more stuff and make modifications. And it's like she didn't order it that way. You can't add the RAM. And that's it. And I thought, wow, that's terrible. And now they've got it so you can't even do it, even if you take the whole thing apart and solder in the RAM, because there's no place to solder it. And I thought, well, what are they doing with the RAM? I don't understand what is going on with the RAM. So I wanted to dig a little deeper into that one. And so that's kind of where I thought we might go today. Is trying to understand a little bit more about what Apple is thinking with that M1 CPU and the total inability to add RAM. So one thing we knew about A13 to A14 is they kind of doubled up on the translate look-aside buffers in the virtual memory management unit. And they did that for the L1 cache, and then they did it for the L2 cache. And I said, man, they got a lot of translate look-aside buffers and a lot of pages there. And the pages are fixed, sized blocks of memory. And I said, well, that's interesting. And how many pages do they have in M1 now? And I don't think they're telling us. And this is a funny thing, right? I mean, I always say real engineers read data sheets. You want to know what a chip does? You read the data sheet. Intel always published a data sheet. AMD always published a data sheet for all their CPUs. Atmel, Broadcom, everybody publishes a data sheet. Everybody except for Apple. Apple doesn't publish a data sheet because Apple doesn't sell CPUs. Apple sells computers. And the last thing they want you to do is buy their CPU and use it in your computer. So this is their sustainable competitive advantage. So now people have said, oh, look, it's a computer company that's also making its own CPUs. How novel. To which I respond, that's weapons grade polonium. People, when you were making a computer in World War II, making the ENIAC, you didn't run out to Radio Shack and buy a microprocessor, right? You built the whole thing from scratch using tubes in your own architecture. And IBM had been doing that for years, and so did Digital Equipment Corporation and Univac and Sperry and Burroughs and GE. I mean, everybody's been building their own CPUs since the beginning. And it's only recently, like within the last 50 or 60 years, where CPUs have been commoditized and turned into things that you can buy casually and just insert it into systems. So this idea that computer companies should make their own CPUs is not a new idea. I mean, some people have said it's relatively new relative to their lifetimes, but in fact, it's been done before and many times. So I'm looking at this micrograph, and it's segmented nicely, and I'm counting cores, all the different things that need RAM. And I got over here, I got the 8-core GPU, and I got the Fire thingy. I got 4 cores for that, and they're supposed to be fast, I guess, Fire thingies. And that's marketing, right? And then there's this 4-core Ice thingy, whatever that is, Ice Storm efficiency cores. Well, I figured that this is the low rent district where they have the cheap low power cores. And then they got the 16 core Skynet, where the Terminator comes out and it has the emergent consciousness, whatever goes on in there, I don't know. And then somewhere over in here, there's like the RAM, and this is it. This is all the RAM you get. It's right there. And so I got 32 hangry cores, right? The GPU cores, fiery thingies and icy thingies and neural thingies. And they are all going to vie for the 16 gigabytes of RAM. And it's perhaps I'm going to make up a number. Maybe I'm close, 32,768 pages. And that's 2 to the 19 pages. And so it's looking like there's 524,000 bytes per page, maybe. So it's fixed size pages. And maybe that's why you need all the translate look-aside buffers, because you're trying to keep track of all the different pages in this thing called LPDDR4X, whatever the heck that is. 4X channels. Everybody has to share this, right? Sharing is caring, I know, but this is one of those things where you kind of like wonder, how does all that work? And so there, I'm going to focus in a little bit on that 8X16B LPDDR4X channel thingy. And so LPDDR, that's your low power double data rate RAM. Think MDDR or mobile double data rate RAM. So it's a synchronous type RAM. It's very interesting that they should put that in there because that's a low power RAM. Why would you put low power RAM on a desktop? And the answer is probably because the thermal appetite of the CPU is so huge, they can't afford to have high performance RAM. So what do? Well, they quad band it, right? In other words, you take the 4 areas of RAM and you get 4 channels, and you can do queries like a pipeline alternating between the 4 different channels, and that effectively improves your bandwidth. Perhaps 4 channels will increase memory bandwidth by a factor of 4 in theory. So, that's not new. Intel had this for the Haswell CPU. They had a quad channel DDR4 system. So maybe they're borrowing from well known, well understood architectures and putting that into their chip. So this whole thing sits on a chip. Um, and basically, you're getting these memory banks, and you're able to access them in tandem, and you can alternate between them. So you can put in a query to bank 1, and then the next address goes to bank 2, bank 3, bank 4, and then back to the first bank. And so that can improve your overall throughput. So that's not too bad. I mean, you can use relatively inexpensive RAM, run it quad core, quad bandit, and then in effect improve your overall throughput by a factor of 4, and still harvest this idea that you've got low power, relatively lower performance, double data rate RAM. So that's all right. I think that's clever, and it's well understood kinds of things in computer architecture world. So yeah, good for them. But still, you're stuck with 16 gigs until they decide in their infinite wisdom that you need more RAM than 16 gigs. And so I'm looking at, this memory, that's uniform memory. And, we're looking at processor performance here, which seems to go up almost exponentially on a curve here. This is an exponential graph, this logarithmic. And then we see memory, and it's going up, but it's going up much more slowly relative to the processor. And this stops at 2010, but not to be outdone, I pick it up at 2000 and overlap to 2011 a little bit. And you can see where the DDR400s, the 800s, DDR4 comes up next. That's where that's, peaking its head. And the nanosecond access times are going down slowly. Capacity is going up rather rapidly. And there's a latency issues. So RAM is, not getting faster, not that quickly anyway. And the reason it's not clear. I mean, look at this little field effect transistor, right? He's acting as a gate, which allows me to write and read from this capacitor. This is it. That's a bit of memory. This is dynamic RAM because this capacitor is always leaking a little bit of charge, and we have to go through and refresh it occasionally. And that's what makes it sort of dynamic. But the transistor count for this type of RAM is 1 transistor per bit. And you need a transistor and you need a capacitor, and bang, you're done. That's your bit of memory. The rest is like refresh circuitry. And so that's not a bad way to go. I mean, this is dynamic RAM. It's normally meant to be used in this way. And in fact, they've been using it like this since the 70s. So that's fine. And then if you look at the dynamic memory photomicrograph, you can see now these things do take up space. You've got to fabricate yourself a transistor. It's got to have a gate. Right? This is a field effect transistor, so it's not bipolar junction transistor. You've got this little capacitor that's made with a couple of traces, and that's all fabricated into the same silicon. And this is a very typical kind of setup for RAM. And it's, well, for the semiconductor fabrication folks, this is a routine setup. And so what you're doing is you're setting up like I will call it an array of capacitors and transistors, that an array of bits. And you need to have sense amplifiers and row address select lines and column address select lines. And you have to be able to refresh your capacitors occasionally, every few milliseconds, or else the leaking will cause all the memory to go away. And that's typically what we're dealing with for RAM. That's probably what they have. I imagine that's what they have inside of the M1. They don't give me a data sheet, so I can't tell you for sure, but this is my guess. And then I'm looking at this thing, And I'm going, holy mackerel. There's the cache. That's nice and big. There's my neuro thingy and my GPU thingy and my 8 CPUs, 4 fast, 4 slow. Everybody into the fabric. Everybody goes to the fabric, and then the fabric goes bzzz, and all the stuff goes in and goes and comes out there. And so they're all sharing this dynamic RAM, which you cannot expand. And if you want to retrieve something, it has to go through the fabric. So what is this thing with the fabric? What's up with the fabric? Right? I mean, used to be we would put everything on like a data bus, but now we're going to a fabric. How come? Is this a bus? Is this a network? Is it a fabric? Is it a what is this? So I'm like, okay, it's not a new idea. Um, the so-called infinity fabric. This is something that people had been using for some time. You basically have the system controller surrounded by a bunch of hangry CPUs, all attempting to access shared memory. And so they have shared cache memory, they have shared external memory, slower memory. And as a result, um, this idea of going out and getting RAM in advance of, like, say, a few addresses that appear to be present both now and in the future isn't all that unusual. The virtual memory coprocessors essentially try to speculate on the next place the program counter is going to end up and retrieve the RAM in advance and fill up the cache. So this is normal, and here, I'll just leave this off a hook. So it always rings when I'm on in lecture. It's just annoying. So then this is a so-called scalable memory buffer chip, and it kind of acts as the router between the processor and the RAM. And so the processor is essentially accessing the RAM through this well, basically this memory controller. And so we have an intermediate process that governs our access to the RAM. And that kind of, is annoying if you're just one processor. But if you're a bunch of processors, that kind of makes sense. You need something that's going to manage access to RAM, especially if everybody's going to do sharing in an efficient way. But how do you do that so that you don't cause yourself a bottleneck with this so-called scalable memory buffer chip? Right. So this is another example of an architecture that came out of Intel called Sandy Bridge. And what you got here is half a dozen cores sharing the so-called L3 cache. So you got to figure the cores have L1 and perhaps even L2 cache, but L3 cache is a slower cache, and the memory controller can prefetch things in order to fill up this cache and keep the cores all satisfied and running. And they call that the Sandy Bridge architecture. Intel does a very poor job of communicating these things to the general public, but we as computer architects can look into this and say, hey, you know what? It's real interesting to see that, this is not a new idea, that if you put in a lot of cores and they're all hungry for memory and they have to somehow share this cache, we should be able to do that with some mechanism, and the memory controller is typically that mechanism. And Intel didn't just stop with Sandy Bridge on that stuff either. I mean, Intel, they had this so-called Haswell, right? This is a quad-core system, and he had a shared cache and another memory controller. And then he had this other thing called the System Agent and Display Engine and another memory controller and DMI. And they have this thing they call direct memory access. They can go out and do a blind data transfer when they have access to a channel, and then proceed to get data to flood back into the core or into cache and do it without core intervention. So a memory IO controller can be like a little specialized CPU that does direct memory access to various channels in RAM and fills up cache and makes it available to the various cores. So that's an interesting sort of idea. I've got this thing buzzing, excuse me. So now the question is, how does all this work in terms of communications, right? Because now we're dealing with a digital data communication network that's going to go out through the memory controller and get RAM. And so when we think about networks, kind kind of think about two kinds of networks. There's switched and there's unswitched. And now you're getting into kind of the area that you might call just general communication network architecture, right? Because when you're dealing with a network of CPUs and something like RAM that they're all supposed to try and communicate with, they've got to go through some sort of a networking scheme. And so in the switched area of networking, remember there's switched and unswitched, we have the so-called packet switch network and the circuit switch network. And so then if we think about the unswitched side, there's packet radio and satellite and local area networks. Essentially, we're dealing with an unswitched network, right? So that we don't have anything but, we'll call it shared media. So satellites are broadcasting on shared media. Packet radio is using shared RF media. Local area networks use shared media access control layers. And then we have these so-called circuit switched networks, and they can have a dedicated path. And dedicated path means that when I'm talking to you guys, it sounds like I have a dedicated line right into your home. I can call you on the phone. Looks like we have guaranteed quality of service and real-time communications. And that's what circuit switch networks are meant to do. And it's not a particularly new technology. In fact, it's probably the oldest of technologies. And you can see that happening here. That's a switchboard over there on the left. And the person who's doing the switching is what they call an operator. It's just a switchboard operator. And what happens there is you, I don't know if you've ever seen one of these crank phones. I was just looking for one the other day, actually earlier today. Let's see if I can find a nice crank phone. And that's a crank phone. So there's a crank handle on the right. You can't really see it. Here you can. That's from 1901, it says. And that's a cool looking phone, right? So that's a carbon microphone right there. And that's a little headset. And you crank this little handle and generate 90 volts. Goes down a twisted pair that's no more than 3 miles away from the central office and causes a ringing to occur. That ringing occurs over here in, let's get rid of this thing. Over here in the central office, and one of these operators, maybe this one here, will pick it up and go, what number, please? And you'll say, Murray Hill 269, and they'll say, just a minute. And then they'll hook you up to a trunk line, which will go out to another central office, and then they'll say, Murray Hill 69, and then they'll make the other phone ring, and they'll pick it up, and you'll have a direct connection. And that is a circuit switch network. I'll just paste in the phone over here and put it off to the right for future reference. So that's typically what's done. Notice there's no dial here. There's no touch tone pad. It's just a crank, right? You can't dial the phone. The operator dials for you. This is the way things were in 1901. So this is a true circuit switch network, and it is possible to build networks like this, and they give you very good quality, but it takes a little while to set up the connection. But after the connection is set, you can make good use of it. And this is not an unreasonable thing to do if it's 1901 and you can't find a better way to deal with it. So here's a circuit switch network that's been modernized. This one is using stepper relays, and they're automating the circuit switch network using a rotary dial phone. And I was just looking for one earlier today. I should have kept that picture. But if you wanted a rotary dial phone, I'm sure you could find one on eBay somewhere. Yep, there's one. I got one just like this in blue. And it's not even terribly expensive. And so rotary dial phone, can I copy this? No, I have to. What if I just sort of grab picture. Here, rotary dial phone. So you dial the phone and it generates a series of pulses. And those pulses go off into a stepper relay, which is here in the wall of stepper relays. And so if you were to take a look at what a stepper relay looks like, and they're pretty cool looking because they're they're very expensive and fancy and typically used in the phone system. That is a stepper relay. Here's another one. You can actually see a 22 pole relay. That's cool. Actually, that's a great picture. So there's your stepper relay right there. $75. Maybe I should buy two. They're small, right? So with that stepper relay, for every number that you dial, you would expect the stepper relay to increment another position. Then when you dial the next number, it goes to the next stepper relay and so on until eventually it makes a route through the network. So in fact, they were able to automate these unionized Communication Worker of America operators out of existence by using the stepper relay and the phone. And it's not to say they didn't need an operator. It is to say that when you dialed the phone, you became the operator. So you were operating the phone switch. And so that enabled you to have a real physical line from your phone to the other phone. And that connection was made through these arrays of stepper relays. And you can see these functioning and even play with them live if you go up to the Communication and Radio Museum in Windsor Locks, which is very fun for communication nerds like me. And so then what happens later in the evolution of the phone system is you get what's called a virtual circuit switch network, where it appears as though you have an actual dedicated line between one phone and another phone, but in fact you do not. It's virtual, and it's done through a digital data packet network. So then comes, the typical packet switch network, and this is the kind of thing that we're most familiar with. This is Ethernet, and it's giving you a bus topology, and that's probably okay for different computers communicating with one another, but it doesn't give you the kind of high performance you need from inside of a CPU. And then here's one called a ring topology network, where you grab a token. They call this a token ring. Then you have control of the network until you are done, and then you release the token, and then someone else gets control of the network. And so this is a way in which you can get a high performance network. So here comes the secret. Right now the screen reveals the supreme excitement. Everybody into the time machine, the fabric system, and go in and somehow come out here into the RAM and get the RAM stuff and bring it in. How does that work? And so we have to do this thing they call examination of the switching fabric. And say, okay, well, what's that about? And the switching fabric is really little more than what's called a cross-point switcher. Very similar to the multiplexer / decoder stuff that we had from before, only what we're going to do is we're going to have a lot of switches. Everything can switch to everything else. And we can have n squared switches this way, where n is the number of inputs and the number of outputs. And so this is an interesting idea. The cross point, that's the thing that's going to grow as a function of the square of the number of n elements in and m elements out. And so you can basically see this is kind of a thing that's going to grow in a, well, let's say, a fairly fast fashion. It doesn't give us a robust level of growth. We don't like n squared things, but in fact, it will allow anything to communicate to anything else. And that enables us to effectively route our requests. But if you have 32 cores and you need access to 32,768 pages, that's a lot of cross points. And so I'm not quite sure how you would deal with that if you really needed to do something like this. Um, Here comes another version of a fabric, and you've actually been able to play with this using your DE2 cards, because you may have used the DE2 Quartus card in Digital Design 1, and you probably, if you take Digital Design 2, you'll use the same card. You can drop in a 32-bit Neos processor core into the FPGA of the DE2 card, and it will use an interconnect fabric to gain access to memory. So that's kind of an interesting thing. This fabric idea is not new. I mean, Apple didn't invent this. And in fact, you wouldn't want them to deploy something that only they had and only they invented, because that's really betting too much on one technology. And, you're kind of betting the future of the company on an untried system or an untried technology. And that's not good. You don't want to take that kind of risk with a new computer architecture. So how does one deal with this so-called high-speed switching fabric, so you can have inputs and outputs, and you can route the data requests to and from these different entities? That is, I think, the secret sauce that goes on inside of the M1 processor. We can only guess what's going on there, but we can make an educated guess about it because we've seen these sorts of things before. There are other ways in which you can create high-speed switching fabrics so that you don't need an order n squared number of cross points in order to be able to gain access to this shared memory. And you do need to have very high speed access to that memory without a whole lot of latency and back and forth, because otherwise it's going to cripple your overall computational throughput, because everything will become IO bound. And that would really suck. And everybody would say these chips are crap and nobody wants them. So somehow, some way, they've been able to give you a high-speed switching fabric without the order n squared thing going on. There's a few opportunities here. You can do cross-point switching in memory. That's the old style way of doing things, where you do everything as a lookup table and decide which way it goes based on a memory lookup. That can be a bottleneck for memory in and of itself. There's a bus style way of doing cross-point switching, and we see this sort of thing in ether switch. And then, of course, there's the crossbar, which increases by the order n squared. But then comes, I would call it, hybrid technologies that give us a mixture of things. And so we'll examine some of those. But the basic idea here in the memory is you're going to hit the bus twice, once to get into the memory, do a lookup, and then again to go out into the output port. So if you're doing ether switch, you are effectively doing this kind of memory lookup, because you're going to have a routing table in your ether switch device. And ether switch devices are quite common. In fact, I have several of them here in the home, and they operate at relatively high speeds, and they're very inexpensive. They're typically unmanaged switches, but if you plug something in spontaneously, they frequently have to be rebooted because their routing tables go stale. And then you can't ping your router or something like this. And you're like, oh, the network's not working. And you're running around rebooting these things. So here comes some packet routing through memory and then routing to an output port. So it's a store and forward system. Here's the bus. You can see right away why buses are an issue. If you use the bus, you're going to end up with bus contention. That's going to give you more IO boundness, and you don't want that because, well, your throughput will suck. And so then here comes the Banyan switch, known as a multi-stage switch. And what this does is interesting. What he's doing is he's going to give you several switches in one stage. And this could be, you could think of this as like a decoder. And then another set of switches in the end stage. And you can think of this as being K on one side, K on the other, N on the in, and N on the out. And then you've got crossbars in the center. And they're kind of bottlenecking things, but in principle, you can route from here to anywhere, and you can route from here to anywhere. as long as you have enough crossbars in the middle. So that can reduce the total number of crossbars, but it also, I'll say, it can also cause some blocking. So here's a coding scheme based on binary. If the bits are 101, then you route down, and then you route straight, and then you route down, and that connects 0 to 5. And then here it says if the input at 1 is to be sent to port 6, what should be the control bits? So here's the input at 1. You want the control bit to go to port 6, which is over here. So it's going to end with a 0. To get down there, this one's going to have to be a, let's see, you go to port 1, you route with 1, then you route with 1, and then you route with 0. So it looks like 1, 1, 0 gets you to port 6. So that's a, a Banyan switch. The alternative, which is to build this giant crosspoint switcher, obviously is going to trade space for time. You're going to need a lot more space to make one switch for every possible intersection, but maybe that's okay if you have the transistor budget. And you can budget a lot of transistors if you're running with 16 billion transistors. I just did the computation earlier today. It's 1 million times more transistor switches than there were ENIAC vacuum tubes. So there's a lot of compute power in that M1 CPU. So I'm looking at the, right, because it was 18,000 vacuum tubes in ENIAC, and there's 16 billion transistors in the M1 CPU. So that's kind of a big difference. I guess if you have 16 billion transistors burning a hole in your pocket, there's an awful lot you can do with it. And now I think Apple is perhaps one of the world's most valuable companies. I don't know if Amazon is more valuable or Apple. I think they trade off. And so there's a compelling argument that the switching fabric could be implemented by any one of a number of ways. The hybrid Banyan system seems like a good candidate. A full-blown cross-point switch is a possible candidate. Not having the data sheet, I can only guess which one they're using, but I'm thinking it's probably closer to a Banyan switch than anything. And so that's a possibility. I can only guess at the architecture internally. There's another way to go. They could have used a time division multiplexed switch, which effectively says we'll send out the packets in one order and then switch in through here and switch in through the other side and do storage forward in the RAM, and then they could change the order in which things come out. And then the time division multiplexer will distribute them to the different nodes. So this is a typical arrangement. It's not unreasonable to do that for an entity that doesn't mind having all of the data go through a single bus. But that'll slow you down, and I rather doubt they're going to do that. This is something you might do with a network. But I don't know if you'd want to do that in a high-speed CPU. Probably not. And now here's a sort of a hybrid. This is a time division multiplex switch going into a crosspoint switcher. So now this is kind of interesting because you're mixing technologies, right? So now I've got the time division multiplex guy switching through in here. I've got the much smaller crosspoint switcher, and now I've got another time division multiplex guy switching in through there. That might work, although it seems too complicated by half to me for the inside of a CPU. For a specialty architecture, that might be okay, though. And so here we are back to the Banyan network. If we have this set up, right, so that we know we're going to do a blind data transfer using a direct memory access, what we'll do is we'll make sure the fabric allows for a route to the from port 1 to port 4 on the left and then to the right. And then what we'll do is we'll get a nice two-way communication with a guaranteed quality of service to the page so that we can get the page and retrieve the page. And all we have to do is rely upon the virtual memory manager to access the page, know how to set up the network for us to gain access to the page, and then it can allocate that page directly to our program. And so what that means is I need to be able to dynamically allocate and reallocate these 32,700 blah, blah, blah pages to all these different Hangry cores, the 32 different entities, GPUs, Skynet, what do we call the Baltic Avenue of CPUs, and the Park Place of CPUs. So somewhere in here we got the fancy places and sort of the low rent CPUs, low rent district. And so that's an interesting idea. I don't know if other CPU manufacturers are going to follow suit, giving you, sort of the low energy CPUs and the high energy CPUs. It's not a bad way to go, I suppose, if you feel like you need to thermally rebalance the computer. It's also good if you're dealing with a mobile device and you need to shut things down, yet keep them responsive with trivial turnaround time. So you move everything to the low energy CPUs, only do the high power ones when called upon. So this is my hypothesis, that the switching fabric is really little more than a Banyan network. Not to dismiss it like this is simple or anything, but it is a architectural design approach which I think might be efficient and which would enable the different CPUs to route efficiently with a minimization of blocking. And once these things are set up with a route, we should expect good throughput from one side to the other. So here's CPU 1 and CPU 3, and they both want memory. And it looks to me like one wants CPU memory from 5, and the other wants CPU memory from 7. And I guess 3 can route down through here and get to 7. But how would this 5 go? I guess he would have to. He can't get to. Well, I guess he can go here and go to 5. So it's possible. It's possible that these two can get to where they need to go, and it's not a big deal. I'm just conjecturing that maybe there's a way that you can envision how there might be blocking. Like what if 3 and 5 both wanted to go to 6 and 7? That would be a problem. So virtual memory managers are essentially going to have to run the show on this one. If we do it right, we'll have good throughput. If the virtual memory manager does it wrong, we're going to be so IO bound, nothing's going to get done. And we'll be, worst case scenario, in a deadlock, because I'll be waiting for you and you'll be waiting for somebody else and they'll be waiting for me and nobody will get any work done. And the whole thing will stall and you'll have to reboot the system. That should never happen, I hope. But that's the kind of thing you have to worry about, right? If you have all of these hangry CPUs and the supervisor who's running the show and keeping everything efficient, the traffic cop doesn't fall asleep on the job, because if you do have a deadlock, there's going to have to be some sort of virtual memory manager policy to break that deadlock, or else it'll be time to look at the spinning beach ball of death and no progress will be made. But if things are working properly, I would hope that it would just have good throughput overall. So this is a question of stability. They're coming up with, I don't know, I'll call it a single point of failure. It's the switching fabric and the virtual memory manager that's managing the switching fabric. And if you get that wrong, you're screwed. And there's nothing you can do about it, because you don't have control of the operating system and nobody wants to tell you what's in the data sheets. So that's an interesting point. I thought, we should look at that a little bit more carefully. I didn't want to get too deep into it, but I did want to look at it and say, this is something that, well, it's kind of interesting. These guys have come up with this idea, right, that everybody goes into the switching fabric, and they won't tell us what's in there. I don't know what's in there, but I can kind of guess. And maybe you guys will be able to, by digging around and looking at the social network maybe you'll come up with a better idea about what's in that switching fabric, and you'll tell me. So that's what I have for my little investigation, another deep dive into the M1 CPU. Hope you'll like that little presentation. Are there any questions? Any ideas about what might be here in this switching fabric? Well, every once in a while, I think what I'll do is I'll do another deep dive into this, into another block here in the M1 release, because it's an interesting set of trade-offs that people are making, real engineering trade-offs. I don't know where I'll go next. I might like to look at this machine learning neural engine, and I have heard that they have an image processing DSP in here, a two-dimensional DSP. Not sure exactly which of these blocks it's supposed to be. These are unlabeled blocks, and they don't always make a big deal about that stuff. But I would like to look into it and see what they have. So that's the M1 so far. And we'll continue with our investigation later. I hope you like that. So how about those phones? I love those phones. So then let's see now. We've got a homework 11, and that's coming up. And maybe we ought to take a look into that. We haven't really looked into it yet. And you guys don't have any questions about homework 10, right? Okay, let's look at homework 11. See what we got. So here's a statement. You know, what is the design rule for the Core i5 processors? Well, you know, you might say, I don't know. How would I find out? Well, just look it up. Look it up. And this is I think I said it was 5. What was it? 14 nanometer. That's not particularly small anymore. And there it is. It's called pronounce that for me, Kaby? Kaby Lake, manufactured using 14 nanometer process. And so it's probably the case that Intel is able to fabricate that on its own, because presently Intel is able to do 14 nanometer in its own in-house. I'm not too sure what Intel is up to in terms of the latest and greatest transistor sizes. I know Taiwan Semiconductor is doing, you know, it's 5 nanometer for Apple and AMD, and perhaps NVIDIA, but the Intel folks, I don't know if they're up to 5 nanometers yet. I don't think they are. At least I don't know of any chips that they've come out with on 5 nanometers. You guys might know. So I think that's true. And so what do we know then? If this is a 14 nanometer design rule, M1 is 5 nanometers. It's got 3 times the density of the transistors over Core i5. So here's one. It says a Core i5 has 5 cores. Boy, wouldn't that be nice? Is that true? Is Core i5? This is interesting because it has you looking at, you know, the Intel chips and trying to figure out what's up. You know, I used to think, boy, it would be great if i3 meant it had like 4 cores and i5 meant it had like 6. i7 meant it had like 8. So if there was some basic idea behind these things, but there isn't. Here it says the number of cores is 2 in a Core i5. 4 threads, but 2 cores. So it's a dual core system. And I'm thinking to myself, man, 2 cores, 2 cores, 2 cores. It's just 2 cores. And now here we go. Now they got 4 cores. So I5 has nothing to do with the number of cores. Well, that's interesting. And then here it is again with 2 cores and 4 cores. And you can't use the model number to determine how many cores there are, at least not in terms of I5. Maybe the part that comes after the I5 you can, but look at this. If there's a 7 after, it could be 2 cores or 4 cores. So he's not giving us any real guidance on this. I think Intel has done an extraordinarily poor job of educating the public, including me, on exactly what it is you can do to determine how many cores there are based on the model number, because it's not obvious. I mean, they went 7400 to 7300. They went from 4 cores to 2 cores. Then they went to 7500, and they didn't change the number of cores at all. And they even got slower. And I'm like, whoa, what happened here? So they're getting model numbers from I don't know where, and they map to performance, I don't know how. And then here comes like another thing here, 6 cores with the i5, 6 cores. So it used to be 2 cores, now it's 6 cores, and it looks like they're all the modern i5s are at 6 cores. So can we generalize at all about how many cores there are based on this idea that we have an Intel i5? And the answer is no. Not unless we know the generation or the year. We can't know. So the answer to question 2 most assuredly has to be false. It can't be true. And then there's this other thing in here, serial communications. So serial communications, we know that's when one bit follows another. And oftentimes we have this thing they call the framing error. And usually what we do is we try to determine when the start and stop of a character occurs based on what's known as a start bit and a stop bit. You can have 8 data bits, 1 stop bit, 1 start bit, or as many stop and start bits as you like. In fact, what you can do when you go and look at how a serial port is set up is you go over into, let's see if we can do this. This is the wrong dialog box. Serial port setup. There we go. You go into 8 data bits. That's the payload. Parity, that's a little overhead that gives you some error correction or error detection. And then in this case, detection. And then here comes the stop bits. That's one of your framing bits. You got to have a start bit, but you also have to have a stop bit. And those start and stop bits help to resynchronize the internal clock on the receiver. And so what you want to do is come up with a mechanism by which you can frame the data and have your receiver clock synchronized with your transmitter clock, even though there isn't a separate clock line. And that's the essence of an asynchronous protocol, that the clocking is built into the framing bits. But if you're sending 8 bits and you've got no parity in 1 stop bit and 1 start bit, you basically have to send 10 bits in order to be able to receive 8 bits, right? Because of that overhead, we say that there is perhaps an 80% utilization available. So what happens with this framing error is you're getting bits that come in that are being read at the wrong moment in time. You didn't synchronize properly. And so if you have wrong start points or wrong stop points, then the bit symbols essentially get out of sync with one another, and then you have a problem. And so, yes, framing errors can be detected with parity bits. This is a basic idea in digital data communications. You put in the parity in order to try and detect the errors and ask for a retransmission. When you ask for a retransmission, that's an automatic retransmission request, or ARQ, and that is also called backward error correction. And it's backward error correction because it goes back to the transmitter in order to ask for the retransmission. Forward error correction, that's when you have an error correcting code instead of an error detecting code. So with forward error correction, what you want to do is you want to come up with a little bit of redundancy so that you can actually correct the errors as they come in without having to go back to the transmitter. So it makes it forward. And applications include satellite communications. Voyager, for example, will do an asynchronous transmission with forward error correction because it's not listening. It's beyond the heliosphere. It can't hear us anymore, but we can hear it, or at least we used to be able to, using the so-called deep space network, an array of satellite dishes pointing at Voyager during encounters. And then as Voyager would transmit the data back, we would correct that error because we couldn't ask Voyager to retransmit. If you have data stored onto a CD or DVD or tape, and there's a little bit of media defect, flaky oxide or schmaltz on the tape or the CD, then you would have a problem reading the data. You can correct that data if you have an error correcting code that's robust. You can't go back to the transmitter because it's basically a defect in the media. So bit slip. Bit slip. Bit slip is the loss or gain of a bit or bits caused by clock drift. That's variation in respective clock speed of the transmitter and the receiver, and that is true, bit slip. So we can have a framing error, which is due to bit slip. That is a drift in the clock. Here's a telecommunications system that's using a baseband communication system. It's not modulating, it's just changing voltages. And these are going into some sort of a wire, which is coming out at the other end. And you can see there are definite timing intervals. And during those periods of time when you sample the data, you would expect it to be stable. This is a so-called non-return to zero line, and that's a binary representation. Usually you use a positive voltage and then a negative voltage. You don't go to zero. That's why they call it non-return to zero. And on average, if the number of zeros and ones is the same, you would not expect this to have any particular DC bias. So that would be a sort of neutral thing. So the answer to that question would also be true. The baseband communication is substantially different from broadband communication. In broadband communication, what you would do is you would use the 1 and the 0, and you would modulate something like a carrier. And then you could turn the carrier from one frequency to another frequency. That would be frequency modulating the carrier. And so if we think about, for example, the Kansas City standard, we went from 1200 hertz to 2400 hertz. That's a form of frequency shift keying. And you could record that onto a cassette recorder and store your programs. So now here's an interesting one. Core i5 has at least, well, 750 million transistors. Is that true? Can we know that? I mean, that sounds like quite a claim. Well, I don't know. I have to look it up, right? And so here we are. Somewhere in here, it should tell us how many transistors are in each one of the cores. Do they give you transistor counts in all of these things? If they don't, we have to look elsewhere. Here it says 382 million. So it doesn't look like that's true. And so that would be false. I mean, it's clear. Initially, these were on a 32 nanometer design rule with dual core. You didn't get that many transistors. If you sped ahead a little bit, to see where they are in terms of transistor count, maybe they'll tell you. I'm not seeing it here. Superfin. Love these names. Super fin. Those are what they call FinFETs. It's a 3D fabrication technology. I'm not seeing a transistor count in any of these things, but I could probably Google it and find out. But in any case, they don't all have at least 774 million transistors. And then it says here the major difference between I3, I5, and I7 is the L3 cache. Well, it's not the major, but it says a major difference. Is that why they're different? So you're telling me I spent all this extra money on an i7 just to get some, I spent all this extra cash to get more cash? That's what I did. And you know what you ought to do with something like this is you ought to verify it. You know, look it up, check out what the cache is looking like. And here it says it's a 4 by 1.25 megabyte cache. And then look up like, I don't know, your i7 processors and see what they're looking at like in terms of cache. They're probably a list of i7 processors. Oh, there they are. And I think if you look at it, we'll see some sort of cache information. And here it is, 8 megabytes of cache. Let's see if it's gone up a little bit. Here's 6 megabytes. So they're basically giving you a little bit more cache. And so that's true. When you start looking these things up, you say, you know, what's the difference between, you know, i3, i5, i7? It's the memory. It's the cache. And they build it into the chip. Now, here's one. It says all i3s are dual core. Well, that should be something we should be able to look up easily, right? You know, what I like the idea of doing is getting you guys sort of familiar with what's out there, just so that you can be, if nothing else, more intelligent shoppers or something. There should be something in here about the Core i3. And so are they all dual core? Well, let's see. Looks like it. Dual core. Dual core. Dual core. Here they are. They're going to 4-core now. So now you can get i3 processors in 4-core. What's this? And the number of threads is 8. All right. So that sounds like a falsehood to me. But it used to be true. It used to be true. So we're going to change that now. It's now false. It's funny how these things change. And this is what happens when you live on the edge of technology. Now, there was 11 attempts already on this. I don't like to change it and make people who are correct incorrect. So what I'll do is I'll say, let's say most, I'll say most, how about most Core i3s are dual core, though lately they have been 4. So that makes it, the answer will still be true. Nobody has to get it wrong just because of that bug. So now let's look at this, this next question here. This is question 9. DMI is the direct memory interface, a proprietary link between Northbridge and Southbridge chips. So what is that? What is Northbridge and Southbridge chips? So you can look it up. And I think it's important for you guys to sort of look at these things up and know. Proprietary link, direct memory interface. So it is a proprietary link. But what do we know about it? It's proprietary. Maybe they won't tell us. Direct memory interface. They should tell us, right? I mean, that sounds like a thing. So here it is. they're back to it's a proprietary interface. It says characteristics of PCI Express using multiple lanes and differential signaling. And it's a bus. Nothing particularly remarkable about it that I can see. It's a bus. Proprietary link. So here is the so-called Sandy Bridge DMI interface. This is double data rate 3 RAM, PCI Express slots, advanced technology attachment ports, extended serial advanced technology attachment eSATA. Let's see what else we got in here. Gigabit LAN connections, Sandy Bridge. So it seems to me like what they're doing is they're separating out the I/O chip from the basic processor. Someone asked, what's the difference between a microprocessor and a microcontroller? Does anybody know the difference? Well, Arduino is a microcontroller, right? Because it's got everything on board. It's got the RAM, the ROM, the I/O, the timer. If you think about it, the only thing you really need to add is a crystal and maybe a voltage regulator if your voltage is bad. But if the voltage is good, you don't even need that. So it's really it's a system on a chip. But wait a minute, isn't that what the M1 from Apple is? Isn't that a system on a chip? It's got the ROM, it's got the RAM, it's got the I/O, it's got the timers, it's got everything. It's got the GPU. Isn't that a microcontroller? And no one will say it is. But if you're just using the it's a system on a chip argument, then yeah, it fits. It qualifies. But maybe it needs too much extra support stuff to be called a microcontroller. So if we look at the ARM processor embedded inside of the M1, it's not really being billed as an embedded microcontroller. Let's take a look. We'll do a quick build, I think. Actually, the way to do this, I'll do it with Tinkercad. You'll like this. This is cool. So what we'll do is we'll create a little digital circuit, something really simple like this one. So here's the Arduino. Now what we'll do is take a look and see, can we replace this with a different CPU? Right. So if I look for basic CPUs, do they have Arduinos here? Basic Arduinos? No. I'll do it with this one. Sorry. I'll go to Circuit IO. This is worth doing just so you can see it, just in case you haven't seen this before. Agree to terms, close this nonsense. And what we'll do is we'll throw in a controller such as an ATmega. And now here we can see we've got the ATmega. It's just one little chip. There's a little extra module for communication that's been added, maybe a couple capacitors, some bypass capacitors for this little regulator. There's my crystal and another capacitor also for voltage regulation. But really, you have the whole system on a chip. In fact, you could probably substitute an even smaller microcontroller, a derivative of the Arduino, known as the AT Micro. And you can see it's really the whole system is on a chip. There's nothing else needed. All the rest is going to be ancillary peripherals. And so that's a kind of a nice advantage to having a microcontroller if you're trying to build something. It makes the construction and design simple enough so that you can wire it up and start using it within an hour or so. That's kind of cool, microcontroller. Whereas we look at something like this and we say there's all this extra stuff on the side, RAM, more interfaces to various devices, and I don't know what the heck this EHCI is. Enhanced something interface, human computer interface. That could be. So anyways, DMA is direct memory interface. Is that true or false? And I think by now we know, yes, indeed, it is true. And we are running out of time. I think we got time for one more question. The Intel Core microarchitecture is a multi-core architecture. So what's that about? This Core microarchitecture. And you should definitely Google this stuff and read about it. You know, it's one of those things where all these different companies come out with all these different sort of new age ways to describe their architectures. And I got to say, it's very difficult for people, even in the field, to sort through all this stuff. So, core microarchitecture returns to lower clock rates and improved the usage of both available clocks and power when compared with the preceding net burst architecture. This is another trademark from Intel. The core microarchitecture provides efficient decoding stages, execution units, caches, and buses, reduces power consumption of a Core 2 branded CPU. So they basically changed the underlying architecture of their CPU in order to be able to support multiple cores. And so this is the key element, you know, when they had to give up on making things faster in order to sell the computers, they said, we're going to use cores as the new transistor. So instead of trying to build computers with, you know, ginormous numbers of transistors or with enormous speed increases, like doubling a clock rate every 2 years, which they had to stop doing, instead what they're going to do is they're going to double the number of cores every 2 years. And they're going to have the so-called core wars. And so from an architectural point of view, there was a basic shift in the approach, and that drove the marketing. Normally, you'd like marketing to drive product development, but in this case, product development had to drive the marketing. And that makes things interesting, right? Because the computer architects basically had to call the shots. They had to say, I'm sorry, guys, you can no longer sell computers based on computers doubling in speed every 2 years. Instead, you'll have to sell them based on, let's say, the number of cores. And so now when we go to shop for a computer, we're counting cores. And we're saying, oh, look, this has got, you know, 8 cores instead of 1. And therefore, what? Maybe it's faster. We hope. So that's what I have for you for today. We're out of time, but we went through a lot of material. I thought it was interesting to explore the M1 CPU, and if people are interested in that sort of thing, give me a thumbs up on that on your little your chat box there, just so that I can know that you're interested in this stuff. And if you are, I'll continue to do a little exploration into the M1, and we can talk some more about it next time. So thanks a bunch, and have a good day.